So example 2. We've got a little different looking function here. We've got g of x equals 1 over x plus 3. So just noticing how this is different. How is it different from example 1? Well, in example 1, we didn't have more stuff in the denominator. Like, we just had x, right? So a couple different things happen in here. Alright, so notice again, I'm giving this to you because I want you to be able to graph and kind of understand what they look like, but the horizontal asymptote is not something I'm expecting you to know just yet. We'll work up to that later. Alright, so the vertical asymptote, let's think about what I talked about in example 1. It comes from making the denominator 0. So if I'm not sure, I could take the denominator, set it equal to 0, and solve. So subtract 3 on both sides. X equals negative 3. So that means, think about it, if I plug in negative 3 right there, what's negative 3 plus 3? It's going to give me 0. So this is a little trick for finding your vertical asymptote, is setting the denominator equal to 0. You might want to write that. Setting the denominator equal to 0 gives you the vertical asymptote. Alright, so x equals negative 3 is going to be that vertical asymptote. That's a 3. Sorry, it's messy. Okay, let's get rid of that. Alright, so we're going to put that vertical asymptote up and down on the x-axis at negative 3. Remember, this is a dotted line. It's this like imaginary line where the function freaks out and can't get a point because it becomes undefined for the output. So it's this dotted line that the function just like jumps across. Alright, and I provided you with the function's horizontal asymptote at y equals 0. So it's horizontal, so it's got to go left to right, and it's the y value 0. So we've got this dotted line, another value where the function is like, whoop, I can't exist here. Gotta jump across this. And then similar to the last one, the two curves for this function kind of fall in these two corners. So my whole point right now is just to kind of give you some visuals of what what rational functions look like and how to draw the asymptotes. So I haven't really gone over how I got these green curves here and here, but we're working up to it. So let's go back to that domain. I did that a little weird in the last example, so let's see how it works on this one. If you're scanning this whole x-axis, right, we're scanning, we're scanning, we're scanning. Is there a value where the function doesn't exist? Yes, at x equals 4. So basically, I've got this whole section of the x-axis where my function's good to go, and I've got this whole section of the x-axis where my function's good to go. It has an ordered pair at that x value. It actually exists somewhere on this curve, right? So how do I represent this red part here? Well, put it in red, this red part right here. Well, we're coming from negative infinity. So we go negative infinity, and we're going all the way up to what value here? Negative 3. And then it's like we skip over negative 3, and we start back on this side of negative 3, and we go all the way down to positive infinity. Alright, so I'm kind of going to erase some of this so it doesn't get too confusing when I talk about the range. Let's get rid of this. There we go. Alright, so now on my range, we're going to look at the y-axis, right? Where does this function exist on the y-axis? So it's all good from here to here, right? And from here to here. Now how am I picking those boundaries? Because I'm looking where this dotted line is. So that dotted line makes me break in my vision of where we have possible outputs. So down here we've got negative infinity. Here is 0. We've got 0 to positive infinity. So kind of looking at that visual is what's going to give me my range. So my function is good to go from negative infinity on the y-axis all the way up to 0. So I'm going to go negative infinity to 0. This notation is not an ordered pair. It is me explaining this interval on the y-axis from negative infinity, like this section of the number line, from negative infinity to 0. Okay, and then we put this u as in jump over this y value, and we're going to include this other section of the number line, which is from 0 to positive infinity. So not ordered pairs, but this is the full range, just kind of explaining what parts of the y-axis and x-axis our domain and range happen at. Alright, so now let's go on to this. So now we're just really going to hone in on what the vertical asymptote is. So you're going to want to write example 3, what is the VA or vertical asymptote? Let's remember, this comes from setting the denominator equal to 0 and figuring out what that value is. So part A, it says f of x equals 6 over x minus 1. Well, what's my denominator? X minus 1. Let's set that equal to 0. And we're going to get x equals 1. Let's think about that. Plugging in 1 here, 1 minus 1 is going to give me 0. 6 over 0 is undefined. It doesn't work. So basically when we're finding that vertical asymptote, we are finding that value that the function kind of freaks out at. So if we were graphing this, we would have a vertical dotted line going through the x-axis at 1. Alright, if you're feeling good about this, I definitely recommend pausing the video and trying B and C on your own. I'm going to keep going though, so pause the video if you would like. So let's go back to this one. So setting this denominator equal to 0. Add 12, x equals 12. So if we're testing that, 12 minus 12 does give me 0. So my vertical asymptote would be a vertical line going through the x-axis at 12. It would be that dotted line. Alright, and now we've got this guy. Great example of really seeing why you might want to set them equal to 0 and work them out. Obviously for this one and for this one, a lot of you guys are like, I can do that in my head. Well, that's awesome. But sometimes you have something funkier going on. So if we set this equal to 0, we're going to add 1, drop down that 2x, and then we divide by 2. So now our vertical asymptote is x equals 1/2. So we would have a vertical line going through the x-axis at 1/2.